All right, sorry for the technical difficulties. For the actual useful part of the talk, I'll turn things over to Tanya here.
Well, I'm Tanya, that's Dan, just in case it wasn't clear. So this is about crypto and some elliptic curves. So we hope this is a gentle enough introduction. If it's too boring, well, it's late in the evening, take a short nap and wake up every once in a while to check whether it's still comprehensible. So why cryptography? So when you use crypto on the internet or for electronic payments, then, for instance, you see an SSL certificate. That's where crypto is in there. If you have an e-passport or an e-identity card, that is using signatures. If you're using TLS to send secret data, then you actually want to have encryption. And so when you have an SSL exchange, then you use, say, RSA or Diffie-Hellman or ECCHacks, and the EC and the ECCHacks and the EC and the ECDSA is what this talk is about today. There's also a huge clump of crypto, which is secret key cryptography, which is really, really cool stuff. It's much, much faster than anything we're going to tell you about today, but it requires that the two parties who want to talk to each other already know each other, that they have done some key exchange. We're going to show you how to do the key exchange, and afterwards, the symmetric crypto. That's what's going to happen maybe next year.
Okay, so within public key crypto, why would you want to use ECC? What has caused all sorts of people to be interested in ECC? The basic answer to that is an attack strategy called index calculus. Now this is, if you want to factor somebody's RSA keys, if you want to break somebody's original non-elliptic Diffie-Hellman, then you use index calculus. It's all sorts of fancy math and algorithms that come into it. And the bottom line is, it keeps getting faster and faster, so we don't even know how fast it's going to end up being. Here's some of the history of when these algorithms were developed. 1975 was one of the first index calculus algorithms, CFRAC, for factoring big numbers. And then there were all sorts of advances, 1977, 82, 90, 94. You've heard about the cryptopocalypse last year, and this is something where this is one of the newest advances in index calculus. That's not something that matters for breaking RSA, but it's just an example of how index calculus, this general strategy, is something that keeps getting more refined, more sophisticated, and faster and faster.
I mean, this is not the whole story. If you look at academic literature, there's also lots of improvements. I mean, we're happy if we can factor twice as fast, but these are the big steps. When you look at the security of two typical sizes of RSA, so there's RSA 1024, which you still see a lot on the internet, and there's RSA 2048, which hopefully your bank is using, then there's two columns of numbers where you can see how much the security has decreased. So back in 1975, so the CFRAC algorithm would still take 2 to the 120 to do the same work that, well, many years later, with a number-filled sieve, so in the 80s, would only take 2 to the 80. So there's a big decrease from 2 to the 120 operations down to 80. And actually, it's not just losing 40 in the exponent, it's much bigger than that. It's something which takes 170 down to 112. So it's not just a linear decrease, it's more than linear decrease in the exponent. So in 85, when basically the number-filled sieve, or the quadratic sieve was already out, the number-filled sieve was in work, Miller was proposing elliptic curves. So as an alternative to factorization-based methods. So factorization or Diffie-Hellman would be broken by all of these algorithms. And then Miller says, well, I've looked at this new primitive at elliptic curves, and it is extremely unlikely that an index calculus attack on the elliptic curve method will ever be able to work. So we can completely ignore all of these improvements, all of these methods that made factorization and fine field-based Diffie-Hellman so much weaker.
Okay, so to get into elliptic curve cryptography, the gentle way to get into it is clock cryptography. Now, this is a picture of the clock. Do you actually have a clock to show people? In case you're not used to what a clock used to look like, some sort of circular thing. If you think a clock is like showing, some digits next to each other, this is what a clock used to look like. For math people, it's x squared plus y squared equals 1.
It's kind of broken, that's why we're late.
The elliptic curves that we're going to show you later in the talk, those do not include the clock. The clock cryptography is not an example of elliptic curve cryptography, but it's really, really close. So we're going to start with clock cryptography, and then once you're comfortable with that, then we'll make one little change, and then that'll be elliptic curve cryptography.
All right, so here's to prove that I passed kindergarten. Here's some points on the clock. So there is the 12 o'clock, that's up there, I learned. Now I also became a mathematician sometime afterwards, and mathematicians like to work with coordinates. So the 12 o'clock point has 0 in the x direction and 1 in the y direction. I know the 1 because it should satisfy x squared, so 0 squared, plus y squared is 1, so y is 1. But there's many more points. So there's also the 6 p.m. There. It's when you start having breakfast, lunch. There's a 3 o'clock point, there is the 9 p.m. point, there is, oh, what's that? I didn't learn that part in kindergarten. So it's half up. If I then look up where the 1/2 goes over, that looks like the 2 o'clock point. Then this is kind of flipping the coordinates. So now x is 1/2, so we're somewhere over here, and then negative. So that would be 5 o'clock, and more points, and more points, and more points.
Wasn't this supposed to be gentle?
Is this gentle?
Okay, so...
Hey, there's some points which I didn't say.
Oh, I'm sorry. So I guess you wanted to tell you about more points like this, 3/5, 4/5. I mean, that one you really have to use some fancy math to see that one has 3/5 squared plus 4/5 squared is 1. That is another point on the clock, and it's not obvious which o'clock it is. You have to really look at your watch to figure that out.
And now he's bailing out of the tricky stuff.
I'm sorry?
Now you're bailing out of the tricky stuff.
Bailing out of the tricky stuff? You mean, okay, you really want me to do the square root of 1/2, square root of 1/2?
No. It's just, I don't know where that point is, but I know it's on the clock.
Okay, you can figure out where the 3/5, 4/5 point is in terms of time. You could make this a little more complicated by parameterizing the clock. So when people take points on the clock, they're thinking of time moving forward, like there's 2 o'clock, 3 o'clock, and you can add those and get 5 o'clock, 2 hours after 3 o'clock or 3 hours after 2 o'clock, and that's 5 o'clock. And here's a picture which is something like maybe that's 1:30 plus 2 o'clock, giving you 3:30, something like that. So those are some points, P1, P2, and P3 on the clock, and you can add P1 and P2 to get P3. And here comes the really horrendous math part, which fortunately we're going to throw away in a moment, which is trigonometry. So if you want to do the point on the clock, which has an angle of alpha, a time of alpha, starting from 12 o'clock, then that point is x equals sine of alpha, y equals cosine alpha. And then if you remember, there were these horrendous trig formulas for sine of the sum of two angles, and cosine of the sum of two angles, and sine of alpha 1 plus alpha 2 is, okay, sine of alpha 1, cosine of alpha 2 plus cosine of alpha 1, sine of alpha 2, and there was something else like that for the cosine. So you can add points on the clock using these sine and cosine formulas.
Now, usually when we convince people to come over to the crypto side, we tell them, well, you can forget all of those non-discrete mathematics. We like discrete mathematics. We're the discrete guys. So there won't be any sines and cosines wandering around. So, well, let's get rid of them. So we don't want to have sine, cosine. We actually would like to work with normal clock numbers. What I have over there with the sine 1, cosine 2, and so on, well, those are just my x and y coordinates. All I said here was that the x coordinate is the sine of alpha, the y coordinate is the cosine of alpha. So then in this whole mess here with the trigonometry formulas, I can just replace every sine of alpha by the corresponding x and every cosine of alpha by the corresponding y, which makes this much nicer, shorter, no trigonometry addition formula. So addition on the clock, if somebody gives you 2 points, x1, y1, x2, y2, then all you're going to do is you take the x coordinate of the first point and the y coordinate of the second point, multiply those, take the y coordinate of the first point, x coordinate of the second point, multiply those, and then add those together. That gives you the new x coordinate. Why? Well, we went through the pain once, and now we can just forget about where it came from. And then we do the same thing with the y coordinate. which is the product of the y coordinates minus the product of the x coordinates.
Okay, so here's some examples of clock addition. We still don't have the computer helping out here, so this is going to be some more painful arithmetic. 2 o'clock plus 5 o'clock, we all remember this is going to be on the test. 2 o'clock was this square root of 3/4, 1/2 that she was talking about at the beginning, and 5 o'clock was 1/2 and minus square root of 3/4. And if you plug those into the formulas there, all right, I'll try this. x1 is square root of 3/4, and y1 is 1/2, and x2 is 1/2, and y2 is minus square root of 3/4. If you do x1 times y2, that's the square root of 3/4 times the minus square root of 3/4, which is minus 3/4. And then the y1 x2 sounds like 1/2 times 1/2, which is 1/4. Add those together, and it's something like minus 1/2. And you do a similar calculation, you get the second part of the result, and you realize that 2 o'clock plus 5 o'clock with these formulas is what you wanted it to be, namely 7 o'clock. And similarly, you can do 5 o'clock plus 9 o'clock, which I think I will skip. Maybe you would have liked to go through that one, but let's try another example. You can take 3/5 and 4/5 and add it to itself. That's what that 2 times 3/5, 4/5 means. It's 3/5, 4/5 plus 3/5, 4/5. And you can just, well, plug those into the formulas, and you don't have to know which o'clock it is. You just get some answer out of that, 24 25ths and 7 25ths. And you can keep adding more and more copies of this point to itself, 3 times 3/5, 4/5. So that's the point plus itself again, and just plug it into the formulas, and you get something with, well, more digits. And as you keep adding more and more copies, you get more and more digits in the denominators there, the 625, and it keeps getting bigger. You can also try adding any point you want without even knowing what it is to 12 o'clock. 12 o'clock was 0, 1. And if you plug those into the formulas, you get 12 o'clock plus 3 o'clock is 3 o'clock, 12 o'clock plus 5 o'clock is 5 o'clock, 12 o'clock plus anything is that thing back again. And that just pops right out of the general formula for adding 2 points. One last example of how you can work with this addition formula. If you take, say, 10 o'clock plus 2 o'clock, that should be 12 o'clock. And, well, 10 plus 2 is 12. If you take anything that's sort of opposite, like that was 10 and 2, if you take 9 and 3, or 11 and 1, anything where it's the same height, same y coordinate, but the x's are negative, those will add together to get 12 o'clock. And you can just try plugging x1, y1 and minus x1, y1 into the formula. Let's try that. If you say x2 is minus x1 and y2 is y1, and you plug that into the formula, then you see the first coordinate of the answer here is x1 times y2 was y1, and then y1 is minus x1 times x2. X2 is minus x1, so you get minus x1 y1 and x1 y1, which adds up to 0, which is what we wanted for 12 o'clock. And then with a little more work, the second part here, y1, y2, that's y1 times y1, and then minus x1, x2, that's minus x1 times minus x1 is plus x1 squared. So y1 squared plus x1 squared, which equals 1. So the second part of the answer is 1. So just a little bit of playing around with additions and multiplications, and you can use this formula to add all sorts of points.
Okay, now let's make this even more discrete. Let's forget about like the circle, which has infinitely many points. You can just take any real number and just take square roots. Let's do this with a very small set of elements. Let's do clocks over finite fields. So I'm now just restricting myself to the numbers 0, 1 till 6. So that's what this F7 is there. And I will also want to add those numbers. I want to multiply those numbers. Now, if I multiply those numbers, say 2 times 5, this is bigger, that's 10. That's bigger than the set that I have available there. If I'm only allowing 6 as the largest number, then 10 is not in the set. So then I will take the remainder modulo 7. So we promised some Python snippets. So here is how we can, for instance, find all those elements. So I'll just run through all x between 0 and 7, all y between 0 and 7, and just check whether x times x plus y times y is 1. If so, I print the tuple xy. And then you push return, and you get those points. And those points, now for the picture, we didn't use 0 till 6. We would like to keep the symmetry. So here we used minus 3 till plus 3. So minus 3 is over here, plus 3 is over here, minus 3 in the y direction, plus 3 in the y direction. So this is the point 0, 1. the same point that we had on the clock before. This is the 1, 0, and this here then is the clock point, sorry, is the final field clock 2, 2.
Okay, if you want to use clock addition with the same clock addition function that you might have written, which we'll show you in a moment, to add points on the clock over the reals, then it's helpful if you can write plus and minus and times, which automatically do this reduction mod 7. And, well, in Python, you can set up a plus and minus and times for an F7 type, an F7 class, which are separate from the usual plus, minus, and times for integers. If you want to set this up, first thing to do is, well, here's an F7 class which will read an integer x and initialize, construct an F7 element, which is that integer mod 7, stored in the .int component of this new instance. For instance, if you take F7 of 7, it'll compute 7 mod 7, and the remainder there is, well, quotient is 1, remainder is 0, and puts 0 into self.int, and then this stir and repper are maybe not the most professional ways of printing things. You might want to print something like print out the fact that this is all mod 7. We're just printing the integer that you get. If you take 7 and initialize one of these things, 7 mod 7 gives you 0. And 10 mod 7, that was the example Tanya had a moment ago, that gives you a remainder of 3. And 20 mod 7, subtract a 7 again, you get a 6. So you can put in anything you want into this F7, any integer you want, you get that integer mod 7. And now we can add in some more functions to F7 instances. For instance, you can have an equality test. Python's default equality is pretty stupid. So you tell it what I actually want equality to do is compare these .int parts of the F7 values, and then, okay, now this F7 type has been augmented with an equality, and you can see that F7 of 10 and F7 of 3 are equal to each other, F7 of 0 and F7 of 2 are not equal to each other. So we got 0 through 6 expressed as the possibilities for the values of a variable with this type. And then here goes the addition, subtraction, and multiplication. What you can see, let's look at the addition, that's the typical case. You take two A and B coming in, and then take the integer inside A, 0 through 6, the integer inside B, 0 through 6, add them together, get 0 through 12, and then put that back into the F7 constructor. And so now you've got 0 through 6 again. And there's some examples at the bottom of, well, 2 plus 5 is 0, 2 minus 5 is minus 3, which is 4. If you're programming in C, by the way, beware, the percent doesn't do the mod that we want mathematically. Python's percent does the right thing. In C, it'll give you negative numbers. Percent in Python always gives you 0 through 6, or 0 through whatever number you took. And 2 times 5, that was that example again of 10, which mod 7 gives you 3.
Okay, so now we have seen a small clock where I could just draw all the elements, where I could just run through, well, 49 elements and try them. Now, everything that Dan just showed with the Python setup, I can replace by 7 by a larger number, say 1,000,003. That's also a prime. And now I would like to define an addition of curve points. So this is just what we did on the real clock before. Now I'm going to plug in elements mod 1,000,003. So I take my points, and I do the x1, y2, y1, x1, x2, and so on, and then I return the points. So let's take an example of this. So one of those many points, I plug in the x coordinate is 1,000. Remember, it's 1,000 mod 1,000,003. And then I check, is there a y coordinate which fits with this? And now in this case, nicely enough, 2 works. Well, yeah, kind of. So if I have 1,000, that gives me 1,000,000 when I square it, and 2 gives me 4. And that's just 1 larger than 1,000,003. So, yep, that's a valid point. So I can now take this point and add it to itself. Just plug in P and P into the addition, that gives 4,007. I can add it to itself again. I can add it again, until I get, say, 6 times the point. So 6 times the point means take the point, plus a point, plus a point. In the end, I have 6 copies, add them together, and I get this point. Now, of course, when you see this, you're like, wait a second, do I really need to do all these 5 additions? No. If I, for instance, had stopped at P3, it's 3 times the point, and then do the addition P3 plus P3, so that's 3 copies, plus another 3 copies, that's also 6 copies. So these 2 things give me the same. So if I want to do this more professionally, here is how I would define the scalar multiplication.
Okay, so this is a recursive function for computing n times p. You have any clock point p and any scalar, any integer n that you want, any non-negative integer n. We're only going to work with non-negative integers here. And you take that n, if it's 0, then you return the 12 o'clock point. If it's 1, you return the point p. 1 times p is p. And then, well, if n is even, then that n//2, Python slightly changing its notation over the years, // is the right way to take an integer, divide it by 2, throw away the remainder. So that n//2, if n is even, that's exactly n over 2. And this recursively computes n over 2 times p, like 3 times p, for instance, if n equals 6. And then does clock add of q comma q to double that n over 2 times p, getting np. If n is odd, then that n over 2 is, well, the n//2 means take away the remainder of 1. You get n minus 1 divided by 2. And then take that times p, double that, that gives you n minus 1 times p, add p to that, that's that if n mod 2 is non-zero, then you add p to q, and finally you get n times p in all the different cases. And then we tried this for some 6-digit number n, which isn't shown here on the slide.
It's secret.
It's secret. And it took something like 30 clock additions, not very many multiplications, to compute n times p. It was very fast, instantly comes out. And there's the answer. There's the x and y coordinates of n times p for whichever secret n it was. And now, it's not so obvious how to figure out what the n is. If you see this n times p, then working backwards to the n, you know what p is, you know what n times p is. You know n is not too big, okay, there's only 1,000,000 possibilities, this is not some really fancy computation, but it'll take a moment to do. It's something where the computer will have to chug along through some computations. And well, maybe you can try to make that faster, but then we could try to make the numbers bigger. Instead of 1,000,003, we could still do n times p when n is much bigger, and the 1,000,003 is a much bigger prime. So there's a little challenge if you'd like to try figuring out what this n is. This is harder than sending an SMS to that phone number. That doesn't work.
All right, now let's assume that we make this much, much harder. So we make it so hard that we feel like we want to use it for crypto. So if somebody would like to standardize clock cryptography, then here's what you do is you start by standardizing a big prime p. So like big, not 1,000,000, like really big, like several thousand bits. And you also standardize a base point. So that means this p on the previous slide. The p where we say, well, we give you p, we give you n times p, we just don't give you n. So let's assume that somebody gives you little p, which is the prime, and this base point, big P, x and y coordinates, which are on the clock. Then what Alice and Bob are doing if they want to communicate, so I would like to send something over to the Bob here.
I'm Bob.
Then Alice picks, well, I pick my secret A, compute A times this base point. Now that's the computation you just saw on the previous slide. It's still visible there, so that's just like logarithmic time the size of of A, and then I send this over to Dan.
And now I guess I have to compute, I take my own big secret B, which I'm not going to tell anybody, and I do my computation of B times that same standard x comma y, and I send back my B times x comma y over to Alice.
All right, so now I have his B times the base point, he has my A times the base point. Now I still remember what my A was. I now take this A and the new point that he just sent me, and plug this point into the scalar multiplication. So I'm doing the same steps, add the point to itself, and sometimes add the point to the point he sent me. So the same steps here, except for now this P is the point that he sent me, is no longer the base point. And this way I compute A times B times P.
Okay, now I get her A times x comma y, and I take my secret B and multiply by the A times x comma y, and I get my B times A times the point, x comma y. And now we've got the same result. Now we've got, she's computed AB times XY, I've computed BA times XY, which is the same thing. They're both A times B multiples of XY, A times B copies of XY added together. And now we use this shared secret to encrypt data.
All right, we also have a picture of this just if we don't make good Alice's and Bob's, so here you see how the message is flying. Now, if you're the eavesdropper, you want to figure out what we've been doing. You can't see what I'm doing here. You can't see what Dan is doing here. All you can see is what's sent here. And you know what the little p is and what the base point is. At least we wish so. Well, so there's some caveats. Don't use just any prime p. Many choices of p are unsafe. Warning 2, this is still the clock. And we said at the beginning, clocks are not elliptic curves, and only elliptic curves are good. So actually the clocks are pretty much the same as doing, say, RSA or find a field when it comes to security. So if you want to match something which is RSA 3072 bits, then your clock needs to have, the prime of the clock needs to have 1536, so half as many bits as the RSA number. That's not actually what you wanted. And then...
Okay, third warning is timing attacks. A lot of you were at the talk earlier about Bleichenbacher attacks against SSL, where a lot of the information coming out of a server under attack, or a client under attack, is from timing. The attacker doesn't just look at the eavesdropping of A times XY and B times XY, the public keys. The attacker sees how long it took you to do computations. A lot of times, the attacker can even see how long it took you for each individual operation that you were doing, because there's electromagnetic emissions or radio emissions or cache effects on virtual machines that affect other virtual machines running under the same hypervisor on the same physical hardware. And then you get to, as an attacker, see all sorts of fine-grained information about the time that Alice and Bob are taking.
You don't really exactly see this computation, but you see the physical effects of this computation. Just imagine Eve's ear is right here. She can hear, she can sense what the computations are doing.
You can actually hear the audio buzz from your CPU if you put a good enough microphone next to it, and that depends on the computations it's doing. There's some real examples of timing attacks here. 2 of the 3 examples that we selected are ECC examples. One of them is the Lucky 13 attack, which was not against ECC, another different kind of timing attack, just to give you the idea of timing attacks are really important. This is a big part of what's going wrong with real deployed crypto, beyond its unusability and other little problems. The fix for this particular problem of somebody seeing the timing is to always do computations in constant time. So no matter what your scaler is, you're not allowed to spend a different amount of time depending on that scaler. And if you just always follow this rule that every secret, you have no secret timing of anything, then the attacker doesn't learn anything. All your timing is public. Of course, it's a bit of a hassle to do computations that way. You can always do it, but it slows things down quite a bit.
All right. I mean, that's easier said than done, but let's go back to warning number 2. Let's assume that constant time implementation takes care of warning number 3. Let's go back to warning number 2. Clocks are not elliptic, and let's turn this circle, this clock, into an elliptic curve. All right, so we take the circle and push inwards. Now, mathematically, what we're doing is we introduce one extra term. Instead of having x squared plus y squared equals 1, we say x squared plus y squared equals 1 minus 30 times xy squared. So this extra term here is the difference between a circle and an Edwards curve, or an elliptic curve. So this particular curve is called an Edwards curve, but it's an example of elliptic curves. Now, if I want to add points now, then let's remember what it looked like on the circle. So on the circle, I had the neutral element at the top. I keep that. So that was the adding anything to 12 o'clock doesn't change the value. That's still the same here. Now here I was just adding P1, P2, getting P3 by these formulas. Now these won't generally work on the elliptic curve. On the elliptic curve, because there is this minus 30x squared y squared, we also need to introduce a little tweak down here. So there's now a denominator. If you take d equals 0, then, well, the formula changes to the circle. And also the addition formulas just change to the circle, because, well, this 30 here is 0, so it's just divide by 1. So the circle comes out as a special case for this elliptic curve. But now we're taking minus 30 and have a nice elliptic curve, and the addition formulas are not much worse. Just a little extra term there.
Okay, you can take, if you want, any prime number p, 7,000,003, something much bigger. You can take any non-square d, that's like that minus 30, Any d that's not a square of anything modulo p. That's something you can check quickly. And then write down the curve x squared plus y squared equals 1 plus d x squared y squared. And this is an elliptic curve. And it's just that extra little d. That's all the extra complication. If you felt like, okay, you understand clock cryptography, then this extra little complication is all you need for elliptic curve cryptography. There's the addition formula, just translated from the math formulas a couple slides ago into Python. Looks very much the same as before, except the x3 and y3 have that d coming in as denominators. Now you might complain about this, saying, wait a minute, when you divide, are you necessarily able to divide? What happens if you divide by 0? Maybe these formulas don't always work. And that's an important point. It's something which you have to watch out for. If you're dividing by something, then you're not allowed to divide by 0. But it turns out that the denominators there, the 1 plus d x1, x2, y1, y2, and the 1 minus d x1, x2, y1, y2, those are never equal to 0. These formulas are complete. They always work, which is what you expect. I mean, you think formulas should always work. It's kind of annoying if there's exceptional cases. But, well, in elliptic curve cryptography, there's actually lots and lots of exceptional cases that people often worry about. And one of the reasons that we like this kind of elliptic curve is that there's no exceptional cases. The addition law is what we call complete. If you look at how the math part of the proof works, then it's important here that that d was not a square. But again, that's something you can easily check. And once you've settled on a d that's not square that everybody can use, then you will never have exceptions in the formulas. If you have your d being a square, then you can write down the same formulas, and most of the time they work, but you have exceptional cases. And we're going to see lots and lots more about exceptional cases. And what's annoying about those is not just, well, it's hard to program, but if you make any mistakes, it's going to be hard to find those mistakes and test for those mistakes. And if an attacker thinks about it more and can give you some points that exploit those mistakes, this often breaks real ECC. So it's better to take a curve where the d is not square, and then you don't have to worry about this at all.
Okay, quick aside, over a finite field, every second d is not a square. So this is not a big restriction. It's just removing half of the possible d's. Divisions are also really slow. So when you implement those, you saw before in the Python script, we didn't even include divisions. We do have them online, but it's like, well, it takes a while. It's unpleasant. It takes even longer if you're worried about constant time implementation. So let's get rid of divisions. It's like, doctor, my knee hurts, and you say, well, don't use it then. But here we actually can avoid using divisions. If you remember how you worked with fractions, a over b plus c over d, then you keep them as fraction. You just multiply the denominators and you cross multiply the numerators and you can add. So we're going to do the same with our points. So we're going to introduce an extra coordinate, the z coordinate, which is just the denominator. So instead of storing x, y as a point, we now store x, y, and z. Where the x and y means the old x and y are x divided by z and y divided by z. Or you can be a little bit more adventurous and actually get somewhat better speed and also introduce an extra coordinate called t, which is x, y divided by z. And if you're interested in how to do this efficiently and actually get computer verified formulas, please visit the explicit formulas database on the link there to see how you actually do the additions then.
Okay. Let's now go back to how crypto looked, but let's replace the clock with an elliptic curve. It just makes that extra little complication in the formulas. There's also an extra choice to make, so it's not just standardize a prime p for everybody to use, but you also have to standardize this d, which is not a square, for everybody to use. This has to be a safe choice. Remember that warning number 1, that there's lots of unsafe choices. There's all sorts of standard criteria that you have to check to make sure that these are safe choices of curves. We'll say a bit more about standards at the end of the talk. Then Alice, as before, has her secret key and multiplies that secret key by x comma y, and, oh, I'm skipping ahead of what this slide says. The slide says that Alice has also Bob's public key, b times xy, and this all sounds just like it was on the clock. Alice now takes the b times xy and then multiplies her a by that, gets a times b times xy, and then remembers that A times B times XY as a secret to use to encrypt and authenticate data. And more concretely, now that we've got elliptic curves, we don't have to worry about an index calculus breaking everything. We don't need to have thousands of bits. Here's some actual real sizes for elliptic curve cryptography, including all the secret key encryption and authentication. The public key, you can have a prime, which is just 256 bits long, and we'll say later that you can squish X and Y into together just 256 bits, and then that reduces Alice's public key, A times X comma Y, down to just 32 bytes that Alice is going to send along to Bob. And then there's a little bit of extra stuff for a nonce, a random number, so you don't end up encrypting the same message the same way every time you send it. Someone would be able to see that encryption repeating. There's also an authenticator so that Bob can verify that the packet is correct. And then Bob receives this packet, says, oh yeah, it's a packet from Alice, there's Alice's public key. If Bob didn't know the shared secret already, Bob takes Bob's secret, multiplies by the public key, gets the same B times A times X comma Y, and then does secret key cryptography, verifies the packet coming in, verifies the authenticator using the nonce and Alice's public key, and at that point has verified that, yes, this is from Alice. Of course, if Bob's never heard of Alice's public key before, then doesn't know who that Alice is, but he gets continuity between the different uses, and then when you add in certificates or other public key infrastructure, you actually know who you're talking to. Everything happening here, all of the public key and secret key stuff, is so fast that we can afford to do this for every single packet going through the internet.
Well, at this moment, we haven't actually told you yet what to use, so here's a safe example. You shut up. So this is a safe example, which Dan shouldn't advertise because it's his own, but I can say it's a good example. So if you take as your prime, a big prime, it has 255 bits. It's a very nice prime, so computations modulo this prime are fast because it's very close to a power of 2. So when you do this mod, this percent operation there, reducing mod this number is very fast, and then D looks reasonably small, and here you have an Edwards curve. Also, here's another Edwards curve. Taking the same D, but just putting a minus there, and putting also a minus in front of the x squared, is another curve. Actually, it's pretty much the same curve. So for every xy that you had before on the first curve, you now have a square root of minus 1 x, y. Same y, slightly different x. So you're just taking a little tweak, it's the first curve in disguise. And actually, we have lots of ways of writing elliptic curves. So here's a whole list of different ways of writing curves. So the first thing that we showed you so far, the clock where you're squishing in the corners, is an Edwards curve. If I now would like to have an extra term here, like this minus 1 here, I generally reserve an A coefficient here, then I can put in minus 1, for instance. That is called a twisted Edwards curve, but then there's also some other things which you still find in the normal textbooks, which are called Weierstrass curves. They look like that. And then there is Montgomery curves, which you can think of as a special case of Weierstrass curves. They have a similar y squared equals x cubed shape, but there are some slightly different terms here. And when you have one of the curves, you can go from one to the other and back. For instance, to go from a Montgomery curve to an Edwards curve, there are other formulas.
Okay, what you'll typically find in standards for ECC for historical reasons.
Okay, stand back, that's going to be horrible.
Is Weierstrass curves. Now here's the addition law, here's how you add 2 points on a Weierstrass curve. Oh, that isn't too bad. All right, there's only 6 different cases. Let's go through them. No, let's not go through them. This is, if you just take one piece of this, then it might seem like it works most of the time. The first formulas work most of the time until you do something crazy like P plus P, and then it doesn't work. And then you have more and more exceptional cases. And some of these cases you don't even realize at first, and then you try writing code for this, and it's just, it goes on, and then you try testing it, and you're not sure you've gotten all the tests right. But okay, that's what you find in ECC standards.
All right. Much nicer than Weierstrass. Montgomery curves is another of our favorite curves. So here you see the entire arithmetic, except for I didn't show you how I will do the constant time conditional swap here. So there is a conditional bit here which swaps the x2 with the x3. we can do this in constant time, just replace this instruction by something which says, well, it stays or it swaps. That's the whole addition on Montgomery. So for every bit, you do these few steps, and you run through the 255 bits that are stated there. So that's another nice case of arithmetic. Note, though, that here we only use an x-coordinate. For the Edwards curve, we had x and y. So there are some differences in what we're doing with them. All right, so Dan announced we're going to talk about standards. So where do you get your standards from? So how to defend yourself against somebody who comes with a mathematician? Mathematicians are scary people that know all kinds of attacks, and if you want to see these attacks, we have some URLs at the end, but we know those attacks, and all of those standards, long list of things, basically agree on certain properties that you want your curve to have. What these standards guarantee you, if you pick one of those standards, then the curve will be secure for the following attacks. Somebody sees the result of your computation, knows the base point, knows your public key, and is not able to figure out what your A or B was. So this is called the elliptic curve discrete logarithm problem, and we have, well, papers over papers to study the hardness of this. So that's what we as mathematicians do, study how hard it is on a certain curve to break the elliptic curve discrete log problem. One thing, for instance, you want that your point, when you add it to itself many, many times, that for a long, long, long time you get different points. Until you get back to the same point, say, after L times you're back, that is the order of the point, that should be a large number. Where large, I mean like 2 to the 250 or something, really large. And yeah, there are all the scripts, so that's one of the criteria, there's many more.
Okay, so let's see, you're an implementer, you take any of these standards, and again, they all pretty much say the same thing, minor differences in details, but they all protect you, and you implement the standard and you say, okay, we're in Germany, let's take the brain pool curves because that's what's used in the German passports. All right, so we take brain pool P256T1, it tells you some big prime number, 256 bits long, it tells you a Weierstrass curve, y squared equals x cubed minus 3x plus something big, and then it tells you the base point, x comma y to use, and then you look at this and realize, ooh, all the nice formulas we were telling you with no exceptional cases, like Edwards and Montgomery, those formulas don't work for this curve. If you have a curve compatible with the formulas, you standardize that curve, then every point you can add successfully, and you just forget about all the exceptions. But you need a curve that works with those formulas, and unfortunately, this curve doesn't work with Edwards and doesn't work with Montgomery. So you have to go back to that messy Weierstrass series of formulas. So, you're very careful. You do exactly what the formulas say. You figure out test cases for everything. You have correctly implemented the Weierstrass addition, all 6 cases, and
timing
you do everything.
invariant.
You do everything constant time, so not going to leak any information to an attacker. And then you have something which is painfully slow, but you're confident about the security until the attacker comes along.
Hi, let's do Diffie-Hellman. Here's my point.
Okay, I'll take my, I guess I'm Alice. Hi. I'm sorry, so now I'm Alice, I've got an A. I take my A times the point that she sent me, which is her public key, and that's not the original x, y, it's some different x prime, y prime that she sent. And I send back my A times that x prime, y prime. And then I've done this computation correctly. And then I've now used the encryption authentication mechanisms that somebody's told me to use, standard mechanisms. And I've encrypted some data and sent that through the network.
I'm on the network. I see his ASG same encrypted message. Now what he doesn't know is that no matter what his A is, there are not actually that many different points. I didn't give him a point on the brain pool curve. I gave him a point on a much nicer curve. Look, it only has a 5 here. The brain pool curve has something much, much bigger here. This is a friendly curve. Also, this point only has 4,999 different copies, which means he's not actually computing what he thinks he's computing.
Oops.
Now, the reason that this works is that in this whole mess of the Weierstrass curve, there's no A6. So no matter whether it's the A6, which is the huge number for the brain pool curve, or the 5, which is the nice curve I gave him, it doesn't matter, he'll just use those formulas. And then the A gives me one of those 499 different points, from which I learn a modulo 4999. Let's do this again.
Uh-oh, she's going to send me another point.
Hi, Dan, here's another point.
So I take that new x prime, y prime, I compute my A times that, I send back something encrypted using that shared secret, and now she does the same kind of computation. She has secretly sent me a point that has small order, and I never noticed that it had small order. So now she's figured out my secret modulo some other number.
And again, and again, and again.
And this happens 20 times maybe, and then she uses the Chinese remainder theorem to figure out my whole secret A. Even getting a few of these leaks is enough information that it does a lot of damage to the security of the system, and, well, if this happens 20 times, then, well, I'm screwed. So what do people normally say in response to this? They say, oh, didn't you notice the footnote in the standard that said when you have a point coming in, you have to check whether it's on the curve, because somebody might have been trying this evil attack. So this is blaming the implementer, which is how we get secure systems, by blaming the implementer. That's good. If something's gone wrong with a system, then it's the implementer's fault for not checking. Don't even get me started on stir copy. You should have checked the length of the string you were oh, I'm sorry, wrong talk. You should have checked that this point was on the curve. You should have checked it had the right order, another kind of attack like this. You should have, by the way, paid patent fees to Certicom. Okay, let's skip
No, just saying, I
part.
mean, if you do this, you might get a phone call saying we have a patent on point validation.
Yeah, so instead of blaming the implementer for not jumping through these hoops, why don't we get rid of the hoops? Why don't we design the crypto? Why don't we design the curves so that it's not actually possible for somebody to screw this up? We know how implementers think. We are implementers. We know what we do wrong, and it's not that creative. I mean, we keep making the same mistakes again and again and again, so let's actually protect against those mistakes and design a system that's robust against those, which for ECC says you take your x comma y coming through the network, don't allow an x comma y to go through the network. Just have an x. And then y was y squared equals something. You could, if you want to communicate y, you can send one bit that says whether it's plus or minus the square root of whatever y is the square root of. Or don't bother sending y at all. Remember those Montgomery formulas don't even need to look at the y. So this, if you just send along an x, then there's very few possibilities for the attacker to choose points, to try to fool you the way that we were fooled a moment ago. There's a couple more of these rules which the curve selector and the protocol designer can put in, which mean that you, as an implementer, have a much easier time. Like the protocol designer can tell you to always multiply the scalars, the A and B, the secrets that you're using for Diffie-Hellman, always multiply those by what's called the cofactor of the curve. There's this base point that has order L, has L different multiples. There's going to be, say, 4 times L or 8 times L points total on the curve. You're only seeing L of them. And to make up for that gap and avoid some other fancier attacks, you always multiply your secrets A and B by 8. And that completely protects you against these attacks. And that's something that can be put into the protocol and tested. And similarly, the curve designer can always choose curves to be what are called twist secure. There's still a little bit of wiggle room if somebody's sending you a compressed point. And this twist security says that, well, basically the wiggle room lets you choose between 2 different curves. There's this curve and then a sibling of the curve, what's called the twist of the curve. And the curve designer can make sure that both of those are secure. Both of those have these big primes. There's an L and a sibling L, and a cofactor, small cofactor, and another small cofactor. And if the curve designer chooses one of these twist secure curves, then the attacker has no flexibility left to fool you. The attacker won't get any information about your secrets A and B.
Well, so then why is this not happening? Well, actually, it's kind of happening. So there is some motion to get like the next generation of EC standards out. So next generation meaning curves where you don't shoot yourself in the foot when you try to implement them in the simplest way. With the simplest implementation is also a secure implementation. Turns out usually when you're on something more secure, it gets slower. In this case, the bonus is it gets faster. Already in 2010, Adam Langley from Google was posting to the TLS mailing list saying, hey guys, elliptic curves crypto has made some advances. Wouldn't it be nice to have like curve 25519 as a named curve? Then not much happened. We did some work proposing good methods to, or well, we think it's good methods, to generate curves. And well, thanks to Snowden last September, there's suddenly some motion coming into this from other people going like, oops, given that the NIST curves have lost kind of their respectability, where we think, oh, maybe the NSA is not just the good guys, shouldn't we have another motion? Luckily, there's lots of other people saying, hey, look, it's not because you're paranoid. We don't know whether the NIST curves are bad from a security point of view, but they're certainly not pleasant from an implementation point of view. We could be faster, we could be more secure. And so there's, well, a few quotations, and there's a draft, and then we make another curve if somebody wants to have really paranoid security level, 417 bits, 400, yeah, and 414 bits, more curves. We have a safe curves page, blah, 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 blah stuff. Finally, okay, CFRG is moving on. There was some NSA guy who was the co-leader of the CFRG, so CFRG is the crypto research working group from the Internet Engineering Task Force, except for the NSA co-chair will still be there to advise them, you know, tell them whom to listen to. Now, the hope was that we could finish this on a happy note, saying, oh, it's all good. Now it's
hey, there's a happy note here. Microsoft has chosen curves. So, you know, once Microsoft stepped in, that's the end of the discussion. Embrace, extend, extinguish, stop arguing. Oh, sorry.
Well, so the final slide would have been something nice, but at the moment it's just the discussion continues. Thank you for your attention.
Thank you very much for our talk. We only have very, very few minutes for Q&A, so please quickly line up at the microphones. We have like 3 to 4 minutes, so be really quick. Short questions only. Don't ask about your thesis, just ask short questions. Okay, mic 2, go.
Are you actually aware of any attacks or weaknesses in any of the NIST 186-2?
Sorry, any weaknesses in, could you repeat the second?
In the curves included in NIST 186-2.
Yeah, so for instance, NIST P224 is not twist secure.
Anything else?
That's the only one that's known to be a problem. Look, all of these are, if you're willing to do the work of implementing very, very carefully, and you check for a point coming in, being on the curve, having the right order, et cetera, et cetera. If you're willing to do a lot of work, have something that's slow and fragile, hard to test, hard to implement, then you can do something secure with the NIST elliptic curves. Then the steps forward that are part of modern ECC are do something that's faster and easier to implement correctly. And that's something that, well, most people are happier with.
Thank you.
Okay, internet, please.
Yeah, very short question. If you were the NSA, could you influence your own standard so that you could break it, and how would you do that?
Well, short answer, the nice thing about standards is that there's so many to choose from.
Is that the answer? Okay, Mike, which one is it?
I mean,
3?
longer answer is, if I'm free to choose, say, the ANSI to the French standard, there's no justification given whatsoever. I can feed you whatever curve I want.
Okay, this mic, I can't see the number because there's too many people.
How do you come up with the key length of 45 bits, and how do you know it's secure? It's just the absence of something like index calculus?
So the key length, yeah, the fact that index calculus doesn't apply is what allows ECC to get away with very small key sizes compared to RSA. And then something like 256 bits, that's coming from saying, well, the biggest computations that someone can do with current computer technology, 10 years from now computer technology, using, say, a 65 megawatt power substation, that biggest computation they can do would still not break a 200-bit elliptic curve. So we feel very comfortable using 256.
So for the attacks that we know how to do, all the numbers are at safecurves.cr.ypto. So there you can see like how many operations 2 to the 200 you need to do for breaking a 414-bit curve.
Okay, we are unfortunately out of time, so please again thank our speakers.